space PNC carries a K-ray metric of positive constant from sectional curvature C. And the open unit ball Bn in the complex space Cn carries a K-ray metric of negative constant from sectional curvature, negative constant C. And moreover, a simply connected and complete K-ray manifold of constant harmonic sectional curvature C is holonomically isomorphic to one of the above domain. This is a beautiful, famous result in K-ray geometry. In Hessian geometry, we explain similar result as follows. Third, spaces of constant Hessian sectional curvature. Euclidean space, the first Euclidean space Rn, D, G. G equal the standard Euclidean vector on Rn. Of course, Euclidean space is a constant Hessian sectional curvature 0. The second case, the Hessian domain Rn dg defined by the potential phi is given by 1 over c log sigma EXI plus 1 inverse, where C is negative constant. In information geography, this formula is very famous. The case 3, Hessian domain omega dg given by omega is a standard paraboloid, and phi equal for positive constant c 1 over c log xn minus half times sigma x squared inverse. This Hessian structure is a constant Hessian sectional curvature, positive constant C. Problem. The NDGB are simply connected Hessian manifold with constant Hessian sectional curvature C. If D or G complete, then MDG is isomorphic to one of the Hessian domains of previous theorem. Recently, Furuhata and Tose gave an affirmative answer for the case C equals 0 and negative constant C. Therefore, it remains the following problem. In the case of positive constant C, then MDG is isomorphic to the paraboloid given in above 7. So this domain, this Hessian domain. The condition D or G is complete is necessary because in the first case D and G both complete. The second case D is complete, that G is not complete. The third case omega is not complete but G is complete. it is a little bit different from Hessian geometry. And the first case is homogeneous. The second case is not homogeneous. Third case is homogeneous. But Hessian case, all constant hollow section curvature, the space of all homogeneous. Therefore, a little bit different. And in the case 2, the Hessian domain is obtained from multinomial distribution. It would be difficult for me to find out this case if I have no knowledge of information geometry. In the case 3, the domain is derived from a certain probability distribution induced from normal distribution. Therefore, second case, the multinomial distribution connected to multinomial distribution, and third case is connected with normal distribution. Therefore, geometrically, multinomial distribution and normal distribution are geometrically in opposite direction, or in opposite situation. Section 5. Let us recall regular convex cone. A regular convex cone omega in Rn admits the canonical characteristic function C such that the Hessian, log Hessian, is positive level. We call G equal d log Hessian the canonical Hessian metric on omega. Let omega be a homogeneous self-direct cone with respect to a certain inner product. Then, identifying the dual space R star and Rn by this inner product. And self-direct cone admits a certain inner product. And identifying the space R star and Rn by the inner product. Then, the gradient mapping iota is a map from omega to the dual cone omega star. But in this case, omega star by the self-duality, omega star equals omega. And iota is symmetry with respect to the Riemannian method G. Hence, the Riemann space omega G is a Riemannian symmetric space. In this case, we define multiplication on Rn. A star B, the component of A star Bi, ith component, equal sigma gamma ijk O aj bk, where gamma ijk O are the value of the component of difference tensor gamma at the fixed point O of the symmetry iota. Then Rn is a compact Jordan algebra with this multiplication. It is well known that the set of homogeneous self-direct cones directly correspond to the set of compact Jordan algebra. algebras. And the compact Jordan algebras are completely classified. Example, spherical cone or Lorentz cone. Let omega be a spherical cone defined by that inequality. Then, omega is a typical homogeneous cellular cone. The invariant Hessian structure DG, where the potential function phi equal 1 over 2 log F inverse, 1 over F. This is the potential function. The gradient mapping user and the fixed point is given by this formula, 1 over fx minus x1 minus xn minus 1 xn. The fixed point O equal 0, 0, 0, 1. Then the Jordan algebra multiplication is given by S sub E equal AN B1 Bn A1 An Bn minus C plus Bn A minus C Shima A1 This is a typical case spherical cone and Jordan algebra. The gradient mapping and fixed point. Section 6. Hessian structures and affine differential geometry. Definition. Affine margin of level surfaces. Let omega dg be a Hessian domain in Rn plus 1. And let E be the gradient vector field defined by Gxe equal d phi e. This vector is used also Professor Koshu. Koshu used this vector field in his paper. Suppose that our level surface M of phi satisfies d phi and d phi not Banshee for all point x in M. Professor Koshu used this vector field frequently in his paper. I learned this idea. Using this gradient vector field as a normal vector 2m. And let us consider an affine margin of M in R plus N by spoil. For tangent vector xy on M, dxy, we decompose dxy, the tangential component dmxy, and the normal component hxye. And dxe is also decomposed into tangential component equal minus sx, and normal component equal tau xe. The first formula is Gauss formula, second is Weingarten formula. And dm is called induced connection, and hxy is called affine fundamental form. S is a shape vector, and tau is a transversal connection form. Laplacian. Let iota n and Gn be the restriction of iota and G to n, respectively. The Laplacian of iota n with respect to Gn d star is, by definition, for independent vector fields x1, xn, the Laplacian iota n is defined by sigma Gij d star xi iota n star xj minus iota n star nabla n xij, where Gij is the inverse matrix of Gn xij and nabla n is the Levi-Civita connection for Gn. Then we have the following theorem. The gradient mapping, the restricted gradient mapping iota n is harmonic with respect to Gn d star. That is, Laplacian vanishes identically. If and only if alpha equals minus half times tau, where alpha is the first cosine form, tau is the transversal connection form, and moreover trace S is shape vector, trace S equals 0. Definition: affine minima. Affine hypersurface with affine numeric C is called affine minimum. If the Konoma mapping nu is harmonic, Hessian proposed the following problem analogous to the Bernstein problem in Euclidean geometry. The following is the affine Bernstein problem. Let f x1, xn be a convex function on Rn if the conormal mapping nu for the graph xn plus 1 equal fx1 xn is harmonic. The conormal mapping nu for the graph is harmonic, then the graph is an elliptic paraboloid This conjecture has been confirmed when the case n equal 2 by 2 Dinger and 1. The general case is still an open problem. But if we replace the role of Konoma mapping U by the gradient mapping U, we obtain a affirmative answer to the similar problem. The affine number C and the Konoma mapping U dual each other dual each other, and the gradient vector field E gradient vector field E and d phi. D phi is a gradient mapping. Gradient vector field E and d phi gradient mapping derive each other. Therefore, if we replace the role of conomer mapping by the gradient mapping iota, we obtain affirmative answer to the similar problem. Analogy of upwing Bernstein problem. For convex function f x1 xn on Rn, we said omega is a domain over the graph defined by xn plus 1 equal fx1 xn. Domain over the graph. And let phi be a function defined on omega by that equation. Then, the Hessian phi is positive definite, and we have a Hessian structure on omega. Note that a level surface of when is just a graph of f. Phi equal constant equal xn plus 1 minus x1 xn equal constant. Therefore, the level surface of phi is a graph of f. Then, the following are equivalent. The gradient mapping iota m is harmonic with respect to G and D star. M star is an elliptic paraboloid. Therefore, we obtain affirmative answer to the similar problem. Section 7. Hessian structure and information theory. We need not lecture this section. Theory. Probability distribution induced by law. That law is be an injective linear mapping from a domain R in Rn into the set of all positive definite symmetric matrices S plus n of degree n. We remind that all positive definite symmetric matrix S time is a typical example of homogeneous self-real cone. For x in Rn and mu in Rn, omega in R, we define a function px mu omega. Then, this is an exponential family of probability distribution on Rn, parameterized by theta omega. Theta is changed from this. The Fisher information metric is a Hessian metric on the domain, the direct product Rn and R with potential this function, phi theta omega. Example. Let rho be the identity mapping from S plus n to S plus n. The probability distribution in this value is nothing but the family of n-dimensional normal distribution. The facial information metric is a facial metric on the domain, the direct product Rn and S% with potential dysfunction. The dual domain omega dash of the Hessian domain omega is given by eta C. Eta in Rn and C is a positive definite symmetric matrix such that C minus half times eta transpose eta. That is a symmetric matrix. That symmetric matrix is contained the positive the cone positive definite that is contained in S plus the cone, spherical cone S plus n. Therefore, this is a kind of real GL domain due to Kotsu. GL domain was obtained by Piates Shapiro to realize homogeneous bounding domain by affine homogeneous domain using homogeneous convex form. And Professor Koshur and Bimbao transfer the notion of GL domain to real reality. And Professor Koshur realized homogeneous convex domain, regular convex domain, is realized as a real GL domain, such a form. The potential of the dual Hessian structure of omega dash is given by determinant that determinant inverse. This is the potential of the dual Hessian structure. Moreover, the following is a simple example. Let rho be a map from positive number, the set of positive number, one positive number, to S%, defined by rho omega equal omega IN. IN is a unit matrix, del N. The Fisher information metric is a Hessian metric on the domain. The potential is given by 5 theta omega. The dual domain of omega dash, the dual domain omega dash of omega is obtained by eta C. Eta in vector Rn, eta in Rn, and C, the positive real number, such that positive number C minus 1, that's a quadratic standard paraboloid. This is a standard paraboloid. And the potential is expressed by simple form rho C minus half term inverse. By the previous theorem on concentration sectional